Yes. Can you hear me? If you can hear me, can you please confirm it? Yes. Hello, students. Can you hear me? Parvez Das, can you hear me? Yes. You are audible. Audible, right? Yes or no? Yes, audible. Fine. Yeah. So just note down the fluid machinery, or basically we call turbo machinery topic that we are going to start today. So is it your first class? Yes, sir. Yes. You can write in the chat section if possible. Yeah. Parvez Das, can you tell me? Is it your first class? Yes, sir. This is my first. Okay, fine. Fine, fine. So turbo machinery basically try to understand this thing in a very, you know, fluid mechanics manner that we are going to solve this fluid machinery topics. So first of all, before this, I would like to give you some brief introduction about this fluid machinery. I think fluid mechanics you have covered from the recording lectures. Yes, covered from the book, not from the recording lecture. Can you please write in the chat section? Actually, I cannot hear your voice. Like, it's not very much clear to me. Can you write in the chat section so that I can come to know whether you have understood this topic or not, like fluid mechanics actually. Yes. I covered. Okay, fine. You have covered from the books. Which book we have followed? So basically, fluid mechanics, we are dealing with the behavior of the fluids or study of the motion of the fluids without consideration of the forces, with the consideration of the forces. Without consideration of the forces and torque, we call fluid kinematics. With the consideration of the forces, we call fluid dynamics. Yes or no, guys? Yes or no? So now, when I enter into the topic called fluid dynamics, so it is a study of, first of all, note on the definition. It is a study of. It is the study of fluid motion. It is a study of the fluid motion while considering the force responsible for it. Yes or no, guys? So when I just talk about the total energy, that whatever we have covered from the Bernoulli equation, and there is a limitation in the Bernoulli, right? When you cover from the very good standard textbook, then you will follow. Then you will find that the Bernoulli's equation is having some flaws. Yes or no, guys? Can you just tell me which flaws we are having? What are the limitation of the Bernoulli equations? So when I just write total energy equation in this form, suppose I'm writing total energy equation as P by rho g plus V square by 2g plus z equal to constant. Yes or no, guys? That means this is my potential energy, or maybe we can call pressure energy. This is a kinetic energy, and this is we call potential energy. Potential energy we generally call spring force as well as whatever the gravity force. So here we don't have any spring forces. So whatever the gravity force or whatever the work done against the gravity, right? That will be stored in the form of what? Potential energy, right? Yes or no, guys? Now, first of all, tell me what is the unit of this all these parameters? Meter, right? Meter. So can I write energy Newton a meter divided by weight of the fluid? Yes or no? Can I write like this?
Yes.
Energy per unit weight. Now you just verify it. Energy is Newton meter, weight is Newton. It will cancel out. The unit is what? Meter only, right? Yes or no, guys?
Yeah.
Perfect. So now just note down. I think no need of that, but still just try to note down the important points. Now we will try to see the classification of the fluid machinery. On what basis basically we can classify this fluid machinery? Tell me, guys. What are all the classifications? Is it over?
Power generating and power consuming.
Very good. Perfect. Can I move to the next slide?
Yeah.
Now, so when I just write about classification, of turbo machinery, so classification will be, generally we can classify under two broad classification. That is the first one, work producing device, right?
Sir, I have one concern regarding not regarding this session. Hello.
Yes, I can hear you.
This is not related to this session. Actually, I want to know when will the general awareness session will be covered. Can you please tell me, because I'm more interested to
Can you
attend
write in the chat
that
section?
lecture.
I'm very sorry, but I cannot hear your voice clearly, very much clearly.
Okay, I'm writing. I'm writing.
Yeah, if you can write, it will be better. So work producing device, and we have the work absorbing device. Meanwhile, you can write in the chat section, work absorbing device. Work producing device will be like a turbine. Work absorbing device, just like what? Pump. So basically we have the broad classification, something like that. Energy producing device, energy absorbing or consuming device. Yes. So this topic I cover, I am interested. Just wait. So this topic I cover, I am more interested in the lectures on general awareness for HL exam. Can you please confirm when the session will be held? See, general awareness, I think you will be, giving the, you will be given the recording session, or maybe already the link has been sent in the group, right? I think sir has sent the YouTube links for the general awareness. Can you please check it out? In the group itself, when you join the group, like I think you might have joined the group of HL. Okay, I will share. Do not worry, I will share. So in that you can find the links for general awareness classes, right? Fine. So I will just send all the again whatever the sir has been sent in the group. Again, I will resend it, right? Fine. Okay. So basically, we have the classification of turbo machinery, work producing device and the work absorbing device. So major classification will be turbine and the pump. Now again, turbine, what is happening in the turbine? What is going to be happening in the turbine? The power is going to be what? Produce. That means whatever the fluid energy is there, whatever the kinetic energy of the fluid will be there, that will be converted to mechanical energy. Yes or no, guys? Yes or no? Mechanical energy in the form of what? A rotor will be start rotating. Whatever the blade will be attached to the particular shaft or maybe hub portion, that particular fluid will be impacted high amount of kinetic energy to the particular blade, and the blade will be start rotating. that rotational kinetic energy will be converted into what? In the form of mechanical energy. Of course, that is the mechanical energy. That mechanical energy will be converted to the shaft power, and that shaft power will be converted to what? Generating power. Yes or no?
Yeah.
Perfect. So this is what the sequence has been happening in the case of turbine. But in case of pump, what is going to be happening? Repeat procedure will be, just reverse procedure will be there, right?
Yeah.
Yeah. But the reverse procedure will be there. That is, there is no doubt. Here we have to give some electrical kind of energy, right? Whatever the electrical energy will be there, that we need to power switch on. Then whatever the mechanical energy will be there, that has been converted to what? Fluid energy. Understanding my point?
Yes, sir.
Yeah. So that is what, whatever the mechanical power, because of the rotation of the blades, the blade will send the liquid to the what? Up to the high amount of height, whatever the height will be there. And of course, there is a difference between pump and compressor. See, compressor is also what? One type of work absorbing device. But there is a slight difference between what? Pump and compressor. Can you please tell me? If I just write
In pump, pump is able to handle incompressible fluid, whereas compressor is able to handle compressible.
it is for liquid, right?
Yes, sir. For incompressible
for
fluid. The
gases,
pump is
right?
for incompressible fluid and compressor is for compressible fluid.
Compressor is for compressible fluid. Yeah, that is correct. But can't we use the compressible fluid in case of pump? With the help of pump, can't we send it? You can also write for incompressible fluid. And here you can write for compressible fluid. One more difference is there. It is used to increase the pressure, right? It is used to increase the pressure of the fluid, right? Yes or no, guys? But here, if you just observe for the in case of compressor, it is used to increase both temperature and pressure, right? Yes or no? Are you understanding my point?
Yeah, temperature increases in compressor.
Yes.
Yes, sir.
Yeah. What you're saying?
The temperature increases in compressor.
I'm not getting. Can you write in the chat section like?
If the temperature increases in compressor, whereas in pump that doesn't occur.
Okay. So now again, in turbine also we have many classification. Yes or no? In turbine also, if I just write hydraulic turbine, of course we have the steam turbine also. Understanding my point?
Yeah, hydraulic is steam turbine.
Yeah. So if I just talk about only about hydraulic turbine, then what are the major classification we have? Can you please tell? What are the major
Hydraulic.
classification? Yes.
Radial flow, axial flow, tangential flow.
Are you sure?
Yeah, it is classified according to the direction of flow, such as tangential flow, radial flow, and axial flow.
Okay. Then can you please tell me the example for those things?
Such as tangential flow, such as Pelton turbine.
Tangential flow. Can I call this tangential flow?
Radio
Yeah,
reaction
just wait.
diagram.
Can I call this tangential flow to be impulse turbine?
Yeah, obviously, impulse turbine we can also say. Pelton and impulse are same.
Now, then can I just call reaction turbine?
No, reaction is different. Reaction is a radial flow turbine.
Yeah, that is what I'm saying. Means in that category, the reaction turbine category, when the pressure and kinetic energy both will be changes for the fluids, then we say what? Reaction turbines, right? In the
Reaction
impulse turbine, what is going to be happening? The pressure will be constant, right? Understand
Pressure
my
will be
point?
constant, only for kinetic energy will be same.
Kinetic energy will be changes. We generally call reaction turbine to be impulse reaction turbine sometime, because here whatever the power has been generated, that has been generated with the help
Actually,
of what? Both the things.
actually both pressure and both kinetic energy changes.
Yeah,
That
that
is
is yeah, correct. Very good. Now just tell me in that category, what will be the example? Here example is only one we have. That is, if I just talk about the tangential flow or impulse turbine, we have major basically chunk. Example is what? Penton turbine, right?
Pelton turbine.
Pelton wheel, basically we say. But can you tell me the example for this?
Uh, for what?
For reaction turbine
Reaction.
or impulse reaction turbine, rather to say.
Francis turbine.
Francis, then what about Kaplan?
A Kaplan is the axial flow. That is not reaction flow.
Francis turbine, right?
Uh,
Now tell me, which is more efficient, Francis or Pelton turbine?
it
Just
is more
think and tell.
efficient.
Yes.
So, please let me think.
Yes. Take your time and note down whatever the things are there on the
Uh,
slides.
I think impulse turbine is more efficient
More efficient, you are saying.
because because in case of Francis or reaction turbine, when the fluid flows over the uh, aerofoil type passage, uh, during pressure reduction, there may be chance of some loss.
Mm-hmm.
That is why when the fluid will be flow over the aerofoil type blade
Okay.
during pressure change, so there may be chances of some sort of losses. That's why I think that that is less efficient Francis turbine.
Mm-hmm. Then, so when I
But
just talk about, wait.
so what is the exact reason? Please say.
Yes.
Uh, what is the exact reason for this?
Yeah,
It is more
I
efficient.
will just wait.
Uh,
Today I'm changing my mic. Just wait. Hello, I'm audible.
yeah, you are audible.
Yeah. Now try to understand. So sorry. The Francis turbine we basically call what? Inward flow,
Reaction turbine. Inward flow.
inward radial flow, reaction turbine.
Yeah.
Inward reaction flow, radial turbine. That means the flow direction will be radial, basically, right?
Yeah, yeah.
Again, yeah. But in the reaction turbine only, we have one more example. Kaplan turbine also. Understand? But the direction will be different. Understanding my point?
Yeah, yeah.
Kaplan turbine, that will be axial flow reaction turbine. The flow will be parallel to the shaft.
Mm-hmm.
Understanding my point?
Yes,
Yeah. So that's the reason. Just note down. One more example is there. I'm just writing for here only. not very much separate case, but if I just include in that only, so that will be good. Major classification will be tangential flow and the radial flow. That whatever you said, that is absolutely correct. But in that, we have, subcategories also. So just note down modern Francis turbine. Nowadays, whatever we are using, that is a modern Francis, that is a mixed flow reaction turbine.
Yeah.
Mixed flow means radial as well as, axial both.
Radial and tangential.
Mixed flow reaction turbine. Now, coming to the question which I asked you, even I did not discuss anything about Kaplan turbine and this Francis turbine, Pelton turbine as well as, Kaplan, Francis and Pelton, but still I'm asking you that a very broad question that which is having the more basically efficiency. That is going to be more clarified when I discuss the reaction turbine and impulse turbine. But for the time being, I'll be just telling you the short answer, right? Whatever you said,
Yes,
it may be correct, but let me just verify with my whatever the explanation will be there, right?
yes, please.
So just note down. If it is done, let me know. Are you noting down?
Yes, sir.
Okay. Once it is done, let me know. So I'll be just because you already covered the portion, so that's why I'm asking the question. Otherwise, I couldn't ask this question because I need to explain whole detail about the pattern being Francis turbine.
Yes,
Right?
yes, sir.
Yeah. Can I move to the next slide?
Yes, sir, please.
Yeah. Before that, just note down the books that you need to follow for turbo machine because that is the mandatory. Because this class is not basically this class will be recorded actually, and that will be uploaded to the YouTube channel. So I need to tell the student that those who are seeing the basically recording lectures. So reference book that you can follow. Of course, Eunice Singhal will be the all-time the great book for the fluid mechanics and basically for all thermal subjects. For reference book about turbo machinery concern, you can just follow DS Kumar for problems, right? For problems, you can just follow DS Kumar. Or basically not problem. Maybe I would say rather than saying problem, you can just follow for theoretical portion or theory. The second book will be R.K. Bansal. Of course, some mistake is there, but you can avoid that. Not in the turbo machinery, I'm talking about the fluid mechanics. Some mistake is there, but for numerical regarding this turbo machinery, you can follow this book. Right?
Sir, actually, I have one query. Sir,
Yes.
actually, in most of these books, such as D.S. Kumar or R.K. Bansal, whatever in this book, the coverages are too much. So that is referred mainly for competitive exams like GATE or yes. But for I want to know which book will be very suitable or perfect for interview purpose, because in interview purpose, mostly practically based practical approach with these questions are asked. Which are not needed in competitive exams like GATE. But whatever the topics are needed for GATE, that
So
are
you're
not
asking
asked in
for
interview.
basically for interview, right?
Interview for.
See, interview
Because in
basically,
interview,
yeah, Singhal you can follow. Singhal is a very good book for all the thermal subject. If you are just preparing for the
sorry.
interview like thermodynamics, Singhal,
Single.
you know,
Mm-hmm.
that is a Eunice Singhal one book is there that of course I'm having the PDF of all the Singhal textbook, right? So that you can follow for thermodynamics. If you are attending any interview, you can just follow for basically fluid mechanics. you can follow for heat transfer also, right? In fact, refrigeration and air conditioning also included in the thermodynamics itself, so that basics will be covered. Because in that book, each and everything will be written in the very, very, prescribed manner, as well as, very, childish language, so that you can understand very easily and you can just explain to the whatever the panel is there who is sitting in the interview. That will also be very comfortable with respect to that also, right? So that will be easy, that whenever you are able to communicate to the panel member in a very, labor manner, so that labor can also understand whatever you are saying, so that they will be giving you full marks. That is what the strategy for among all the basically, interview which are happening, the same strategy will follow, right?
Yes, sir.
Right. So now coming to the reason, there is a very good reason is there for basically, if I'll just talk about the reaction turbine. If I just talk about the reaction turbine, and then if I just talk about the impulse turbine. Of course, you might have studied so that you can correlate whatever the things I will talk for the next few minutes. So there is a soft power we are getting basically when there is a runner power, right? And this runner power will be basically, runner power means rotor power, whatever the rotation will be happening of the blades, right? The blades which are attached to the shaft, that will rotate, right? Because of that, rotational power will be there, right? So from here, now from where we are getting the rotational power? From hydraulic power, right? Yes or no? So within the two stage, 1, 2, within the two stage, we are getting what? Soft power. Understanding my point? Now, suppose for the same soft power, of course, that soft power is coming from the rotational power, right? Or we also say runner power. RP is what? Runner power, right? We have so many components attached to the, hydraulic turbines. It's not only the blades. We have the runner also. That the complete portion path we say runner, right? After that, we are having what? The closed chamber. Understanding my point? Outer cage will be there, right? That sometimes we call diffuser section, right? Now, soft power, then we have runner power. This runner power we are getting in the impulse turbine, not directly in the form of what? Hydraulic power. We are getting in the form of, first of all, kinetic energy, because nozzle will be attached. Understanding my point? This nozzle, whatever things will be there, that whatever the hydraulic power is there, water power is there, that has been converted. First of all, see, this is what we have the storage. Suppose from here the pipeline has been connected. Through this pipeline, we have the nozzle has been connected. Through this nozzle, whatever the things will happen, this will be imparted into what? Blades. So that the whatever the nozzle is there, this is the nozzle. This is the what the pipe is there. This is what the height. So through this particular height, whatever the hydraulic power is there, mgh, that is going to be impacted a lot of amount of energy, but that is happening through the nozzle. A lot of nozzle has been placed around the, basically runner of the particular what? Pelton turbines. Basically, we are not placing more than 6 because of what? Efficiency losses in the nozzle. Now, this nozzle is going to have some kind of efficiency. Every instrument is having some efficiency. That cannot be perfectly 100% efficient. Now it is having efficiency. So first of all, whatever the hydraulic power is there, that has been converted to kinetic energy. That is, whatever the mgh is there, what is the efficiency of the nozzle? Whatever the kinetic energy that has been coming in the form of water power, that has been imparted its energy to the blades, this blade, divided by mgh. Now, if this thing will be there, definitely I need to write hydraulic power, then kinetic energy, then rotational power, or maybe runner power, then we can write soft power. Understanding my point? So here we are getting same amount of soft power in 3 stages. 1, 2, 3. Understanding?
Yes, sir.
Now, when we are getting in 3 stages, then what is happening? Same soft power we are getting 3 stages. Suppose then which is going to have the higher amount of efficiency? Reaction only, right?
Reaction turbine.
See, whenever we have the more stages, more losses will be there. Remember, more stages, more losses, right?
Yes, sir.
Right. So just note down, this is an important reason. So that's a very broad, basically things are there. In the reaction turbine, we don't have nothing called nozzle. If nozzle is not there, whatever the hydraulic power will be coming, that hydraulic power will be converted to what? Directly to the what? Runner power, right? And that runner power will be converted to what? Shaft power. Understanding my point? Yes or no?
Yes, sir.
Perfect. Just note down. Once
Yes,
it is
sir.
done, let me know. Yeah?
Noted.
Noted, right? Now, so again, when I just talk about the basically when we going to start the turbo machine, before that we need to clear some fundamental thing about the impulse momentum equation, because without impulse momentum equation the things will not be done actually in the turbo machinery. So what is the impulse momentum equation?
So, the impulse momentum equation is the rate of change of angular momentum between the inlet and outlet of blade is equal
So
to the torque energy.
rate of change of momentum, that is directly proportional to what forces, right?
Yes, sir.
Whatever the force will be there, that is nothing but rate of change of momentum. That means if I just write in the equation format, momentum is what? Basically m into v, right? So force I can write mass flow rate into, now v final minus v initial. That depends which force you are calculating by difference. Suppose you are adding v final minus v initial. Vf is nothing but v final, that is a final velocity. Vi means suppose that initial velocity. Suppose. Then what is the force, my dear friend? This force we call, this force, suppose I'm taking one example. I'm taking example impact of jets. Did you cover this topic?
Yes, sir. Okay.
Perfect. So in this also we will see a lot of things, and that will be beautifully explained, that impact of jets, like when the jet is vertical, when the particular plate is what, vertical or horizontal, incline, or maybe it is having some curvature, then what is amount of force that has been exerted. Now let me just tell you example. There is a nozzle. Through the nozzle the water has been coming out. Now this has been exerting the force onto this particular plate. Now basically, now suppose that this is a plate. Because of the water forces, this plate will try to move to the what? Right direction, right?
Yes, sir.
Now to hold on that, we need to apply some kind of forces. This force will be called force exerted by plate onto the fluid element, right? And whatever the water forces will be there, that I'm going to call F1. Let me call this to be F2. Of course, F1 will be equal to F2, but the direction will be opposite. Understanding my point?
Yes, sir.
So if I just write F2, that is the force exerted by the plate onto the jet. This is what? Jet of the fluid. So what I'm writing? The force exerted by the plate onto the jet, What will be the formula? Mass flow rate into V2 minus V1. Now, sir, what is V2? Sir, what is V1? That is what the next question. Now try to understand the points which I'm mentioning right now. The point number 1 will be coinciding with the axis, and the point number 2 will be what? The outer edges of the what? Plates, right? So 1 is the entry point and 2 is the exit point, right?
Yes, sir.
Now, so just note down the things. Now, if I just write force F1, of course, magnitude will be same, but the direction will be different. So force exerted by jet onto the plate, that is going to be mass flow rate into V1 minus V2. So note down, very, very important. The force exerted by the jet onto the plate will be just opposite of the force exerted by the plate onto the jet. But remember this notation, whenever you are calculating the force exerted by jet onto the plate, initial minus final will be there. But if you are calculating forces exerted by the plate onto the jet element, then it is final minus initial, right?
Yes, sir.
Right. So just note down. So one by one, we are going to discuss the cases, right? When we are discussing the cases, then I will tell you how the development of the Pelton turbine has been happening. Why the bucket? If you just observe the bucket of the basically Pelton turbine, it is something like this. Why it is something like that only? Why it is not like this? That is also one of the very beautiful question we have, right? Those things we will cover very comfortably in this particular turbo assembly. But before that, let me explain you the different cases so that we'll be jump to the what? Cases what? I think we have the 5 to 6 cases. Among that, the last case will be what? For Pelton turbine, right? Understanding my point?
Yes, sir.
Now, once it is done, let me know.
Yes, sir. I know.
Note it down.
Yes, sir. No.
Done.
Yes, sir.
Okay. Now try to understand. The case number one, which I'm going to discuss, the case number one, which I'm going to discuss is when the jet strikes stationary flat plate, then what is going to be happening? Now, for this case, let me just write down the example for the figure for this particular case. Now, the water is coming out from this nozzle, and there is a plate, vertical plate, and this plate is what? Fixed, my dear friend, right? So this plate cannot move to the right direction by the application of what? Force by the jet, right? Now tell me, what is the initial velocity? 1, 2, 2. What will be the initial velocity? Tell me, guys.
1.
V1, right? Whatever the water is coming out with the velocity, that will be V1. Now tell me, what will be the final velocity, my dear friend? Let me call V1 to be what? V. Whatever the velocity with which the water is striking this particular plate, that is called V. This is what we have the nozzle jet through which the water is coming out. Now tell me, guys, what is going to be happening over here? Or let me just take you the basically what? This jet is forming the diameter to be what? T. Now tell me, after striking the plate, this water will be taking the shape like this or not?
Yeah.
So initially, whatever the velocity is there, what will be the final velocity in x direction? See, whatever the formula we are writing, force of the jet onto the plate element, mass flow rate into V initial minus V final in the x direction only, not in the y directions. So here, after striking, it is moving like this. Check it out. It is just moving like this. So finally, whatever the velocity is there at the point 2 is 0 in x direction.
Yes, sir.
Right? So what will be the force exerted by jet onto the whatever the force exerted by jet or stream of fluid onto the plate element? That is the mass flow rate into V. Now, how to calculate the mass flow rate? Rho into Q into V. Now, how to calculate the Q? Q, you know that whatever the velocity is, whatever the discharge is coming from the nozzle, the same velocity, discharge will be coming out from the jet also. So directly I'm writing Q will be equal to pi by 4 d square into velocity with which it is coming out from the nozzle, right? Basically, it is coming out with the velocity V, but in the nozzle, it is going to have a different velocity, right? Here, maybe it is going to have some different velocity. We are not bothering about that, right? So here, basically, we can write Q is equal to area into velocity. Area of the flow into velocity, so A into V into V. So what is the force exerted by jet? Rho into A into V square, right? Check it out. In the x direction, whatever the force exerted by jet will be this one. Yes or no, guys? Check it out.
Yes, sir.
Perfect. Just note down, very, very important. So here, whatever the impact is there exactly at the middle point. So sometimes we call symmetric bleeding conditions. Symmetrical condition I am giving you so that it is striking exactly at the middle one. Whatever the velocity is coming through which through the nozzle, it is just striking at the center line of the plate. Now, what is the forces in the y direction? Whatever the force you have calculated, of course, that is fine. But when you are fixing this one by some reaction, by some hinge joint, it is going to have the reaction forces in the x direction as well as in the vertical direction. This will be the reaction forces that you are calculated, that is fine. But what about the vertical reaction forces, my dear friend? For that, we need to find force of jet in the y direction. Am I right?
Yes, sir.
How to calculate that? Tell me. First of all, tell me what is the answer for this question?
Zero.
What?
Zero.
Zero, you're saying?
Yes, sir.
Why zero?
Because at the inlet there is no momentum in y direction.
But can you prove it
And
out with the same whatever the equation we are just writing? Mass flow rate. See, force of jet basically can I write initial momentum minus final momentum?
Yeah.
Can I write like this, my dear friend?
Yeah.
When I can write like this, then initial momentum will be suppose mass flow rate in the y direction. What is the initial velocity at the point number one? At the point number one, there is a no vertical velocity. All the velocities are what? Horizontal velocity. So that is zero. Minus, understand. What will be the final momentum? Final momentum will be half of the mass flow rate is happening in the positive direction. Half of the mass flow rate is happening in the downward direction. Check it out.
Yeah.
So can I write mass flow rate by 2 in the vertical direction? I'm going to take the positive. Suppose I'm taking the positive. Now it is moving with some velocity v2. V2. So I can write v2 minus mass flow rate divided by 2. Sorry, plus, because half of is what going to be split it out. But here it is going to be, what is going to be happening? Plus v2 or minus v2?
Minus v2. Minus v2.
Minus v2 will be coming out so that it will cancel out. So force exerted by the water onto the plate will be zero in the y direction. Understanding my point?
Yes, sir.
Check it out. Perfect. So just note down very, very important thing. What is the work done? What is the work done that you have calculated in the engineering mechanics? Horizontal forces into velocity of the blade. Yes or no? The blade moving with what velocity? That is called blade velocity. Let me write here, blade velocity. Of course, my dear friend, the blade velocity is zero because it is fixed one. If that is going to be zero, this is not equal to zero. So for whatever the work done is there, that is going to be zero, right?
Yeah.
Note on this thing, very, very important. So are you understanding what is happening?
Yes, sir.
Perfect. Again, I will be giving you the question for one more case. You try to solve it, right? For next 2 minutes, you try to solve, then I will give you the solution for that. Understanding my point?
Yes.
Right? Now, instead of considering the stationary flat plate, let me just take you the movement of the plate. Now, the plate is also moving with some velocity called u. Sometimes we call blade velocity. Here, blade is not there, plate is there, vertical plate, so we call plate velocity. Understanding my point?
Yes, sir.
Now, is it done? Can I move to the next case?
Yes, sir.
Perfect. Now, try to understand. It's one of the very important case. Jet strikes the moving flat plate. Case 2, jet strikes moving flat vertical plate. Now I will be giving the option also, do not worry. So now this is a nozzle, now it is striking. The jet of stream I'm just representing by the lines. Now this plate is going to be moved with some velocity u. Suppose that. I'll be asking you so many questions that you need to be very, very careful. Now here I'm considering the point 1, point 2, point 2. What is the point 2? Exit point. What is the point 1? Entry point. Right? Yes or no? See, entering point, leaving point. Right? Now, so here I'm going to considering the jet, which is striking the moving vertical plate, which is moving with some velocity u. Calculate the jet force. So I'm giving you the option, very, very important, rho into. Now this basically the movement of fluid will be, suppose that you can take V1. The jet velocity, inlet jet velocity is moving with some velocity V1. So rho into area of jet. That is a pi by 4 d square. I'm not writing completely. Rho into A into none of the above. Now you try to solve this first question. Second question will be, what is the work done by jet? So again, option I'm giving you. Let me give you the options. The same option, but you know that the velocity of the plate will be multiplied. So V1 minus 2 whole square into U. V1 minus U whole square into 2U. U minus 2 V1. V1. This is what we have V1 whole square into U by 2. None of the above. Take your time for both question number 1 and question number 2 and try to solve and let me know the answer. Remember, this question is not that easy as you are understanding. Little bit of conceptual thing will be required. Of course, answer will be getting. There's no doubt. But still, I will be asking you so many questions.
I think you have option
You can write
4.
in the chat section with the question number and option like 1A, 1B, 1C, 1D.
Sir, I have wrote the answer in the chat box.
Yeah. So what is the answer you are getting?
So
For the
for
first
question
question.
number one, for question one, the option is B, and for question two, option is B.
B.
For question number two, the option is B for Delhi, and for question number one, option is B for Bombay.
Okay, correct. Now why these options are correct? Now try to understand. So here I'm going to consider the same thing, that is impulse momentum equation. I'm going to consider impulse momentum equation. I'm going to consider. Now let me give the answer for first question. Force exerted in the horizontal direction will be mass flow rate. Mass flow rate. Now tell me what will be the formula for mass flow rate. First of all, that is what the importance of this question. Very first thing.
So rho A into V1 minus V.
Yeah, just wait. Let me add this slide. Now this is one of the very important question. A lot of assumptions has been made, but that has to be clarified. So this is the nozzle. This is a jet of stream that has been striking to the plate like this. This is moving with some velocity. So this is my inlet point 1, 2. 2 point is what? Outlet point. Now try to understand. Try to understand. Now, my dear friend, what will be the mass flow rate? Rho into A into V1 or what? Tell me, guys. Here the total velocity is V1. That is the jet velocity, right? Yes or no? But my dear friend, you already know in the vector format that first whatever the velocity is there, suppose this will be the velocity, suppose that blade with which it is moving, suppose that U1. Then what about this one? VR1. What is the VR1? Relative velocity at the inlet. Why we are getting the relative velocity? Tell me. Why we are getting the relative velocity? Because of this vector V is equal to vector VR plus vector U. Understanding my point? Absolute velocity will be velocity, relative velocity plus blade velocity. Understanding my point? Tell me, guys. What is the what is the velocity? What is the velocity of? See, suppose that you are suppose you are writing any point velocity, P point velocity you are writing with respect to Q. Then what you are writing? Velocity of P with respect to Q will be velocity of P with respect to Q plus velocity of Q also. Check it out. The same manner, what you are going to write? The velocity of jet will be velocity of the jet with respect to blade plus velocity of the blade. Understanding my point? What I'm saying? Yes? Tell me, guys. Yes? Yes or no?
Yes, sir, I got.
Yeah. So that is what the relative concept is coming over here. So now if somebody will be asking you, what will be the inlet triangle for this case? This is the case number 2. Like so many triangle we will draw, that velocity triangle we say in case of Pelton turbine, in case of what? Francis turbine, in case of Kaplan turbine. But for this particular case too, if somebody will be asking you the inlet velocity triangle, see these are the question only, interview questions. These cases will not be there in any of the textbook. But the thing is that you need to understand with the basics of vector, because vector is very, very fundamental thing. If the fundamental thing is not clear, they will understand. Hi-fi thing you will not be able to understand while coming to the industries. So they want you to basically with clear, fundamental things. So inlet velocity triangle will be like this. U1, VR1, and that is going to be total V1. Understanding my point?
Yes, sir.
right? Now, coming to that, what will be the outlet velocity triangle? That is what the next question. Tell me guys, very interesting. But one more interesting point, sir, you have taken inlet velocity, whatever the inlet velocity of the blade, you have taken U1, inlet velocity of, let me not call blade, let me call plate. Then what will be the final velocity? What will be the final velocity? Will it be more? Will it be equal or will it be lesser than that?
Will be lesser than that.
Yes.
Yes, sir.
Lesser?
Yes, sir. Lesser.
No. U2 will be equal to U1, my dear friend. That is equal to U. Now, you try to understand. You try to understand.
Okay. Okay. Yeah. Sorry, sir.
Very basic assumption that we are going to consider. The point number 1 and the point number 2 are on the same horizontal plane, right?
Same horizontal plane.
Consider it is the blade is placed in the horizontal plane. So Z1 equal to what? Z2. So that is what the first assumption. Please note down. Assumptions that we are going to follow is Z1 equal to Z2, right? Right. And second assumption we are going to consider frictionless plate. There is no friction on the plate. Understanding my point?
Yes, sir.
Assumption number 1 and assumption number 2. Very, very important assumption, my dear friend. Somebody will be thinking that so it is a vertical flat. Of course, I have written vertical. No, that has to be, I think, not correct word, right? Just note down the flat plate. Understanding my point?
Yes, sir.
Yeah, just note down the flat plate. That's it. This flat plate has been placed in the horizontal plane, not in the vertical plane, right? So that the point number 1 and point number 2 both are having what? The same height, right? Z1 equal to Z2 only. Yes or no? Just like that. Point number 1, point number 2, and this has been reference point. So this is just like a horizontal one, so height will be same, right? Yes or no? It is placed as on the horizontal plane. From the horizontal plane, the reference height will be what? Same only, right? Yes or no, guys? Yes. Yes or no? Now, what will be the outlet velocity triangle? That is what the next question, my dear friend. Tell me. What will be the outlet velocity triangle?
Right angle.
Yes.
Right angle triangle.
Right angle triangle. Why the right angle triangle will be formed? Why the right angle triangle will be formed? See, ut is having velocity like this. Am I right?
Yes, sir.
That is, the blade is moving in the positive x direction. There is no doubt. But my dear friend, the velocity of the fluid with respect to blade is moving in the what? Vertical direction, right? Right? Check it out. Velocity of the fluid with respect to blade is moving in the vertical direction. Check it out. Can you please check it out? So now you join by the vector addition. What the vector addition is saying? Suppose vector A is equal to vector B plus vector C. Then what we do? Vector B, vector C. Then we join this thing by the vector C. Am I right? Vector A, right? Check it out. Check it out. Please check it out.
Yes, sir.
Right? Now try to understand. I'm joining my different, sorry. I'm joining this vector to be, suppose I'm calling this to be VR2. This I'm calling VR2. The relative velocity of the fluid element with respect to blade. That is VR2. That is our relative velocity at the outlet. And now let me join. This is a vector A. Suppose, let me call B vector. This is what we have the vector C. This now we have to join this by what? Another vector that will be my absolute vector V2. Check it out. Velocity of the fluid will not be in the vertical direction, not in the horizontal direction. It will be in the inclined direction. Check it out. No problem, no problem. You can leave for the day, right? Now, so these are the situations that we need to first of all understand that whatever the outlet velocity triangle will be there, that will be taking the formation of what? Right angle triangle, right? So whatever you said is absolutely correct. Now, coming to the next segment, whether VR2 will be equal to VR1, that depends on the assumption that we have followed. We have followed frictionless plate. We have followed the assumption frictionless plate. When we have assumed the frictionless plate, then VR1 will be equal to VR2. Understanding my point? VR1 will be equal to what? VR2. That is going to be questions. Now, what is the force exerted by the jet onto the plate in the horizontal direction? That we need to find. So the now outlet velocity triangle is also clear. So this is what VR2, this is what U2, and this is what we have, V2. What is the V2? Final velocity of the fluid. Now, I think you have noted down, right? Now try to understand the next segment. The force exerted by the jet onto the fluid element in the x direction will be mass flow rate. What is the mass flow rate? The mass flow rate will be rho into area of the jet into what? Relative velocity. Relative velocity. Because whatever the fluid is coming out from the jet, that is not going to exert the same amount of basically what velocity that which is coming out from the this particular nozzle. But the thing is that the plate is also moving. So now what will happen? Condition is that now this is also moving, the plate is also moving. Now what is the effective velocity with which it is striking? That will be V minus U. And that is V minus U is what? VR only, right? So that is what the mass flow rate will not be rho into A into V1, that will be rho into A into what? VR1. Of course, A is what? Area of the jet. Area of the jet. That is one of the very important things that you need to understand. Now, the force exerted by the jet in the x direction will be the mass flow rate, whatever the mass flow rate that has been striking, with what velocity it is striking, with what velocity it has been striking. Now it has been striking effectively with the velocity called VR1. VR1 minus with what velocity in the x direction it is leaving. Effectively it is leaving with the what? Effectively it is leaving with the what? 0. Then what we can write? Rho into A into VR1 whole square. That is what the force exerted by jet onto the floor, what basically plate in the x direction. That will be the answer. You can also write rho into A into V1 minus U whole square. Now, why we are adding U1 in the form of U? Because U1 equal to U2 will be equal to U. So please make a note of it. This is a very important segment. So this is the first method. In the first method, what we did, we just placed the observer onto the plate itself. We have just placed the observer. The observer is sitting onto the what? Plate. That means the reference plane, the observer is just sitting on the reference plane. Now the observer is moving with the velocity called what? The plate velocity. So it is not going to feel any velocity. It is not going to feel any velocity. The final velocity will be 0, right? So that is the first method. Now the second method will be more interestingly for you guys. Now try to observe. The observer is not sitting on the what? It is not sitting on the plate. It is just outside of the plate. It is just observing from outside. Now, if you just observe from the outside, so what is going to be force exerted by the jet in the x direction? Mass flow rate, initial momentum. First of all, it is going to striking the fluid element. It is going to strike the plate with the velocity v1 minus mass flow rate. With what velocity the fluid is leaving with the this particular blade in the x direction? With the velocity called u2, and of course it is equal to what? U only. So again you are going to get what? Same answer, my dear friend. Mass flow rate is what? Rho into A into v1 minus u whole square. This is what we have, Newton. Please note down the force exerted by the jet onto the basically plate, that will be observed by the what? First method, the observer is sitting on plate. Here observer is sitting on what? Outside. Observer is sitting outside of the plate system. So now just note down very important thing. That means what you are doing, observer is just sitting, my dear friend, the observer is just sitting onto the plate. That means the plate will become a stationary kind of thing. The plate will become just a stationary kind of thing, and the water is striking with the velocity called VR1. That means for this case, it is just like this. The water is coming out with the velocity called VR1. Now it is striking the fixed vertical plate. Now it is striking with the what? Fixed flat plate. The water is coming out with the velocity called VR1, and now it is striking with the velocity called what? VR1 to the what? Fixed plate. When the observer is just sitting on the plate, but when the observer is what? Outside, it is observing absolute velocity of the fluid element in the x direction. In the x direction, initially it is moving with the what? Velocity v1. Finally, it is moving with the velocity what? u2. That is equal to what? U only. So both the method answer is same. The work done will be the force in the x direction into what? Velocity of jet. Velocity of plate. So with the help of that, you can calculate rho into A into v1 minus u whole square into u. That is going to be, answer for this question. Now, once it is done, let me know. Now, try to observe the next case. The case number 3. The jet strikes on moving inclined plate. Now, when the jet is striking on the moving vertical plate, then what is going to be happening, that we need to observe. What is going to think that is going to be happening on this particular case, that we need to observe. Now, try to observe. Suppose water is striking this. The jet of stream is coming out from the nozzle. Now it is inclined to what? The inclined plate. For this, we need to draw the inlet velocity triangle and outlet velocity triangle. Of course, I'm going to take the same notation. Initially, water is suppose that the blade is moving with some velocity called u, or let me call u1 equal to u2 equal to u, because this particular plate is there on the horizontal plane. So it is going to be u1. It is going to be what? u1. So inlet velocity triangle will be same, and combined together we call V1. That is going to be same. There is no doubt about it. But my dear friend, here, of course, the mass flow rate will be same. Rho into A into VR1, that is equal to rho into A into V1 minus U. That is going to be same thing here also. But first of all, we need to calculate. This is the point number 1. This is the point number 2. This is the point number 2. What will be the outlet velocity triangle? The point is moving in the horizontal direction like this. The plate, the fluid is leaving with respect to plate. The relative velocity of the fluid with respect to plate will be like this. Will be like this only. That is my VR2. Now from the vector addition, what will be the velocity with which absolute velocity of the fluid that with which it is coming out from the basically what plate? It is going to be V2 like this, right? So what will be the velocity triangle? This will be my velocity triangle, my dear friend. The same case you can draw for here also. It is something like this, U2. This is VR2. It is going to be something like this. Of course, U2 equal to U1 only, so there is no doubt about it. So for this case, the point number 1 is here and the point number 2 is here. The point number 2 is here. This is the nozzle. Jet of stream is coming out, that is striking on the plate, something like this. And now it is going to be, so U1 equal to U2 equal to what? U. Coming to the next segment, we need to find the force exerted by jet in the x direction. We need to find the force exerted by the moving jet onto the fluid element, on the plate element that has been moving with the velocity what? That has been moving with the velocity called U. So mass flow rate, you got it. That is a mass flow rate, you got it. Now, first of all, we have to calculate the normal force with which it is striking the plate. So normal force will be something like this. Suppose that the normal force will be what? Something like this. So if this normal force is inclined to like this, what will be the component of VR1 in the normal direction? What will be the component of this is VR1. Now this plate has been inclined theta. This plate has been inclined with the angle called theta. This plate has been inclined with the angle called theta, suppose. Now what is going to be happening? What is going to be happening if this is my theta? This is my theta. This is my 90 minus theta. So this will be 90 minus theta. Now from the triangle law, what we can write? From the triangle law, what we can write? If this is the VR1, this will be VR1 sine theta. This will be my VR1 sine theta, right? If you're just going to write something like this, one component will be coming out like this, one component will be coming out like this. So theta, this will be the theta, this is VR1. So this is what? VR1 cos theta, this will be VR1 sine theta. So try to follow the first method. The first method is saying that observer is sitting on the what? Plate itself. When the observer is sitting on the plate, it will be just assuming that the plate is stationary and the fluid is striking with the velocity called relative velocity VR1. So force exerted by the jet in the x direction will be mass flow rate with which the water is striking, relative velocity at the inlet section. But we are calculating not in the x direction, we are calculating in the normal direction, first of all. So in the normal direction, it is just a plate. The water is coming over with the velocity called VR1 sine theta. And the final velocity will be what? in the x direction will be 0. In the x direction will be 0. So that is my first approach. So VR1 sine theta. So rho into A into VR1 square into sine theta. That will be my normal component of the force, Fn. Now that will be the normal component. What will be this normal component in x direction? If that is going to be theta, if this is going to be theta, this is also going to be theta. So what about this component? This is what I am having, Fn component. Now if I'm going to resolve in the x direction and y direction, then what I'm going to get it? What I'm going to get it? This will be 90 minus theta. So this fx will be Fn into sine theta. And Fy will be Fn into cos theta. So here what I'm going to get, Fx will be Fn into sine theta. So what I'm going to get, Fx will be, that is force exerted by the jet in the x direction will be, Fn. What is Fn? Rho into A into VR1 square into sine theta into sine theta. So rho into A VR1 square into sine square theta. That will be the final answer. Please note down the final answer. Rho into A into VR1 square into sine square theta. That will be the force exerted by the jet in the horizontal directions. But like in the previous cases, we have seen that the force in the y direction is 0. But in this case, the force in the y direction will not be 0, my dear friend. Because force in the y direction will be force exerted by jet in the y direction. Because what? Because of this Fn component, the force will be coming out in what? Both horizontal and vertical directions. So what will be the answer? Fn into cos theta. So we can write comfortably rho into VR1 square into sine theta into cos theta. That will be the answer for Fy. Right. So note down the case number 3. That is a very, very important case. Once we understand these cases, now we can move on to the what? Moving when, a blade, a curvature blade. Now, before moving on to the next question, we are going to solve some of the questions for previous year paper that has been asked. Now, note on the questions and try to solve it. Note on the questions and try to solve this particular question. A 6 centimeter diameter horizontal stationary water is having the velocity v1, that is 40 meters per second, is tracking a vertical plate. The force needed to hold the plate if it is moving away from the jet at the velocity call 20. That is, a u is given as 20 meter per second. Now, the velocity v1 with which it is striking the plate, that is 40 meter per second. Now they are asking what are the force needed. See, because when the nozzle is coming out in the form of jet and now it is striking the plate which is moving with the velocity called u, then what will be the force that will be needed? We know that the force exerted by jet in the x direction will be mass flow rate into VR1. So now if you just calculate force exerted by the jet in the x direction will be rho into A. Rho is what? 1000. Area is what? Pi by 4 d square. 0.06 whole square. V1 minus U, that is 40 minus 20 whole square. So now if you're just going to calculate, and let me know the answer. So you'll be getting what? 1130 Newton. 1130 Newton. That is option called C. That is the force with which it is striking, my dear friend. C. With which it is striking. But what will be the opposition force? This will be opposition force that is going to be required. Opposition force or reaction force will be opposite of that. So what will be the reaction forces? Minus 1130 Newton. Of course, they are asking only magnitude, so we are not bothering about the sign. So based on the standard sign convention, this is going to be plus, this is going to be negative, right? Now, moving on to the next question. A 75 mm diameter jet, water jet having the velocity called V1. Remember, it's not a nozzle velocity, it's a jet velocity. That means from the nozzle, from this nozzle, the jet is coming out. So this is what will be the diameter, final diameter. With respect to that only, we have to calculate the area. So V1 is what? 12 meter per second. Is impinges on a plane which is inclined, which is just inclined with the angle called 60 degree. Theta has been given 60 degree. Normal to the plate. Normal to the plate. The impact on the plate will be what? They are asking what will be the impact normal to the plate. That means they are simply asking me Fn force, and Fn force we already derived by the formula called rho into A into V1 V into R1 square into sine theta. Sine theta, right? Of course, 60 degree that we need to consider. Of course, they have given very small trick they have played. They have mentioned that the smooth plate is inclined at the angle 60 degree normal to the plate. See, this water is coming out. The water is coming out from the jet, from the in the form of jet from the nozzle at an angle normal to the plate 60 degree. This velocity with which it is coming out in the form of jet and normal to the plate, this is what the normal to the plate. This angle has been 60 degree. Then what about theta? 30 degree, my dear friend. So theta is not 60, theta is 30. So that is about the small trick in this question. Nothing else is there. So now rho is what? 1000. Pi by 4, 0.075 whole square. VR1. What is the relative velocity? V1 minus U1. Right? But they mention whatever the cases we have seen, that is a very simple case. Right? Whatever the question right now we are solving, that is simple case. But we have seen already a big case, that is moving plate, moving inclined plate. But they are asking, my different stationary plate. Simply put, U is equal to what? 0. So what will be the answer? V1 square. So simply 1000 into pi by 4, 0.075 whole square V1. What is the V1? 12 square. So Fn will be 317.925 Newton. That is going to be answer. So C option will be correct. So that sort of thing that is a very, very important while solving the questions. Now, moving on to the next segment. Now, before solving this particular problem, try to observe this question. A nozzle which is connected to the hose pipe like this. The nozzle has been attached to this particular hose pipe, something like this, which is having a diameter 80 mm at one end and 40 mm at the other end in the form of jet. Now they are asking when it is discharging the water, that is 1200 liter per minute, that is 1.2 meter cube per minute. So that is the discharge value, my dear friend. That is what we have, the discharge value with which it is coming out from the nozzle. The force on the joint at the base of the nozzle, they are asking. The force by the joint, suppose this nozzle has been there in the joint only here, then what is the force they are exerting on the joint, basically on the base of the nozzle, basically on the base of the what? Nozzle in the horizontal direction they are asking. So simply they are asking the force exerted by the fluid onto the joint. See, whatever the pressure of the pressure forces of the fluid onto the joint, reaction forces will be coming out from the joint also, right? So indirectly magnitude will be same, but the direction will be opposite. That is going to be, we will take care of those things now. So by looking at the figure, the water is going to move in the same direction in the what, but in the horizontal direction only. So whatever the joint reaction is coming, that is going to be coming in the what, in the horizontal direction only. So whatever the force that has been coming out, force of the joint, directly I'm writing rho into q, that is the mass flow rate, final velocity minus initial velocity, because I said you the force exerted by the plate onto the fluid element will be final minus initial. If you can check it out, the initial session for this particular class, initial movement, whatever we have observed, that is final minus initial. So what we can write, rho is what, 1000, q is what, 1.2 by 60, final velocity that can be calculated, my dear friend, from the discharge formula, a1v1, that is equal to a2v2, put the value of q, get the value of v1. So v1 will be what, 1.2 by 60, area is what, pi by 4, d1 square. What is the d1 square? 0.08 whole square. So if you're going to calculate, you'll be calculating 3.978 meter per second. Now if you just going to calculate the v2 value, so that is going to be q divided by a2. So now once you calculate, you'll be getting the value 15.915 meter per second. So now if you're going to put 15.915, 3.978. Now if you just calculate, this value is coming out to be 240 Newton. This question has been asked in engineering services to the 19 paper only. So now engineering services also, they don't have any, we don't involve calculator there. Calculators are not allowed. And the same pattern will be followed in the HL examination also. So relevancy is what? Is still maintained. Now we need to see the cases where we have the curvature blade, right? Now, before discussing this Pelton turbines and all, we will discuss the case number 4. We will discuss the case number 4 and we will see what we can get it from that. Now this jet is coming out from the nozzle. Now it is striking this what? Moving vane symmetrically. First we are going to consider symmetrical strike. Then we are going to consider unsymmetrical strike. So first of all, what will be the symmetrical strike that we need to consider? Now the blade is there in the form of curvature like this. It is now it's striking with the velocity, and now it is this blade is moving. You call vane or blade, both are same thing. So now jet strikes symmetrical moving vane. Symmetrical means striking at the center. Whatever the water is striking, that is exactly striking at the middle, exactly at the center point. Striking at the center, my dear friend. Now, so here what is going to be happening? What is going to be happening? This is going to be point number 2. This is going to be point number 2. This is going to be point number 1. One by one, I'm going to draw the velocity triangle diagram. Of course, it is going to moving something like this because it is there in the horizontal plane. Now, when you consider this particular case, there is a slight difference between what we are observing in the cases previously that we have seen. Inlet velocity triangle will be same. There is a first of all U1 will be there. Then there is a what? VR1. And of course, we have what? V1. Notations are same. V1 is what? Inlet jet velocity. U1 is what? Inlet blade velocity. And VR1 is what? Inlet, what we say? Inlet relative velocity of the jet, right? Now, you can write over there. Inlet relative velocity of the fluid. With respect to blade. You call blade or you call vane, both are same thing. And of course, one of the more assumption we are following that I'm going to write because those things are very, very important for analysis of the flow through this particular vane. The major assumptions we are going to follow is what? Smooth vane. Very first is smooth vane. There's no friction at all. VR1 will be equal to VR2. Suppose if it would have been mentioned the rough vane, then VR2 will not be equal to VR1. In that case, VR2 will be lesser than VR1, and that value is going to be K times of VR1. That K value will be given to you in the problem itself, and that we call coefficient of friction. That we call coefficient of friction. That is one of the very, very important assumptions that we are going to follow. If it is have been mentioned that assumption is mentioned what? Smooth vane, so we are going to follow this thing. If it is mentioned rough vane, then we are going to follow this thing. Of course, K value will be given to you in the problem. Now try to understand the picture scenario. When the U1 cannot be equal to U2, in which case the U1 cannot be equal to U2, when the flow has been happening like this. Check it out. So these are the very fundamental thing that we are observing, my dear friend. Very, very fundamental thing that we are observing. When the fluid is coming out at point 2, when the fluid is coming out, so fluid is coming in at the point number 1, suppose the radius is what? R1, and point 2 radius is what? R2. From the center point of the shaft, the fluid is coming at the entry point 1. What is the velocity of the blade? In that case, R1 into omega, and outlet velocity of the blade will be R2 into omega. But here, my dear friend, what is going to be happening with respect to shaft? Whatever the blade has been attached, my dear friend, the point is not at all changing. Suppose it is going to be striking at the point number 1 only. There itself we have the point 2 also. Just like that. Water is coming at the same point and leaving at the same point. Water is coming in at the same point and leaving also at the same point. That is also very, very important consideration, my dear friend, that we need to consider while having the analysis. These things we have to consider. Now let me just make you clear with respect to this thing by one more example, so that things will be will clarify to you. Just wait. Just wait. See, so by this example, you come to know that U1 will not be equal to U2, but suppose it is just entering at the same point and leaving also from the same point. Point 1 is here. Suppose point 2 is what? If you just see this, basically what? When you see the front view of the blade, then you will come to know that by this Pelton will profile of the blade will be what? Something like this. In that case, water is coming in and just coming out at the same radial location. At the same radial location from that center point. R1 is going to be what? Same R2. In that case, velocity will be what? Equal to what? U1 will be equal to what? U2. That's the reason I'm saying that. That is what happening over here in this particular case, right? So please note down very, very important thing. Now, now we need to find the force exerted by the fluid element onto the basically curvature vane in the x direction. That we are going to see through this one example. So inlet velocity triangle will be already shown to you. Now try to observe the final velocity triangle diagram. This is my blade profile. Now this is what the relative velocity with which the water will coming out from with respect to blade, like this, my dear friend. That I'm going to call VR2. This is going to be V2, U2. Now what will be the absolute velocity? The absolute velocity will be something like this. This will be my absolute velocity called V2. Now let me call some angle. Let me just take some angle. This I'm going to take the angle call. Suppose now the water is coming out from this at a deflection angle phi, something phi. So this will be my phi. And let me call this to be outlet velocity angle will be, fluid angle will be beta, right? And again, here also going to be same thing. VR2, U2, and then we are going to have V2. So here what is the angle? Phi. Here what is the angle? Beta, my dear friend, right? So that is what outlet velocity triangle will be formed. So this is what VR2, V2, and then we are going to have this thing to be what? U2. So this is what we have phi, this is what we have beta. So please note down, this is a very, very important segment. Outlet velocity triangle. Because if you are not able to form the outlet velocity triangles, then you will not able to solve for the problems. So mass flow rate will be rho into A into VR1. That is the mass flow rate with which it is striking the plate, the vane. Now force x direction will be mass flow rate. Initial momentum will be VR1. Now what will be the final momentum? Half of the mass is going in this direction, half of the mass flow rate is going in this direction. So mass flow rate by 2. Whatever the velocity with which it is coming out in the x direction will be what? VR2 cos phi. VR2 cos phi. But that is going to be what? In the negative directions. Sir, why it is different from previous cases? Sir, why it is different from the previous cases that we have seen? Try to observe. Try to observe. In the vertical plate, whatever we have seen, that whatever the outlet velocity triangle has been formed, try to see how we have developed the formula. How we have developed this particular formula. VR1, that is what velocity with which it is coming out in the x direction. But in this case, why we have not taken this component? See, this velocity, relative velocity is what? In the vertical, in the horizontal direction is what? 0, my dear friend. In the horizontal direction, it is 0. That's the reason we have taken what? 0. Check it out. The same thing I'm going to follow here also, my dear friend. In this particular case, whatever the cases I'm showing you right now, the same thing I'm going to follow. Inlet relative velocity, observe. For which method I'm going to follow? The first method. Of course, which method I'm following? The first method. What is the first method? Observer is sitting onto what? Observer is sitting onto what? The vane itself. Observer is sitting on the vane itself, and it is just observing that the plate is stationary or the vane is stationary and the water is striking with the velocity called VR1, not V1, VR1. Now, because you will look at, suppose you are sitting on the plate, you are sitting on the vane and you are looking at the water, you will think that, okay, it is moving with the velocity called VR1, not with the V1, because you cannot see the absolute velocity. You are sitting on the plate itself, vane itself. If you are sitting outside, then only you can see the individual absolute velocity. Right? Apart from that situation, you will never understand, you will never gonna see the absolute things. You will always see the relative phenomena. So inlet velocity, VR1, right? Simple funda is that whenever we are going to consider the plate is moving or vane is moving, suppose that vane is also moving, simply remember one thing. Simply, of course, here U2 is what? U1 itself. U2 is what? U1 itself. Simple, remember one fundamental thing, that always we have to take the relative velocity whenever the plate is moving. When the plate is not moving, only velocity of the water is there, only water is moving, then absolute thing will be there. But when that, see, you are sitting, you are suppose is standing on this platform, and now the train is moving, my dear friend. Suppose you are standing on the station, suppose you are also moving, and the train is also moving with the velocity. Then suppose what will be the observation will be there? What will be the observation will be there? You can see your own velocity as well as train velocity. Suppose you are sitting in the train itself, you cannot observe your own individual velocity. You will always see the relative velocity, my dear friend, with respect to train and you. Suppose you are running on the train, you are inside the train and you are also running. You will always observe the what? Relative speed, my dear friend. The same thing we are going to follow. You are sitting here itself, and when you are sitting here itself, you will always find the relative thing. Now, when you try to solve, suppose when you are trying to solve this thing, plus mass flow rate by 2 VR2 cos phi, because here also it is going to be what? In this direction, and that is going to be negative, that is going to be negative. That is the one thing. Now, my dear friend, now it is symmetric, so we have considered this thing. Fx will be what? Rho into A into VR1. Now you are going to solve. Of course, we are considering the smooth vane, so VR1 will be equal to what? VR2. So VR1 square we have taken outside, so it is going to be what? 1 plus cos phi. So Fx will be rho into A into V1 minus U whole square 1 plus cos phi. That will be your answer. Please note down, very, very important. Of course, Fy will be 0. You can try it out. Just try to take the inlet momentum in the y direction. That is 0. Final momentum, that is going to be cancelled out, because half of the mass flow rate is coming out in the downward direction and half of the mass flow rate is going in the what? Upward direction. Both will cancel out. The work done will be Fx into velocity of the vane. That is going to be give the work done, my dear friend, right? So I hope that you understand today's lecture. We are going to consider we are basically focused in today's lecture about the velocity triangle, how to form it, just based on the what? Vector conditions. In the next segment, we are going to see the Pelton turbine, Francis turbine, and Kaplan turbine. Then we conclude the session by the centrifugal pump, right? Thank you all.